So let's look at an example of using the complex Fourier series. Now we're going to use the square wave here, and we're using this for a particular reason, because once we've worked through this example, we can use this in order to create an intuitive derivation for the Fourier transform. So let's get started on this. We've got a function, and it's a little square wave. The period is given from as t0, so that's from this point here to this point, or equivalent, you could say this point to this point. And the pulse width is given by a distance τ, so we could call that positive τ upon 2 and minus τ upon 2. Now we've seen the derivation of the complex Fourier series, so what we're doing is we're approximating a function f of t using a series of sines and cosines, and the sines and cosines have been wrapped up into one complex exponential function e to the in omega naught t, and we've seen that we're able to work out the coefficients Cn by using this equation here, and we've seen this equation here as in effect a dot product, and the orthonormal basis is going to be given by this function here, which is the e to the minus I n omega naught t. So let's go ahead and we'll apply this here to the example above. So the values of Cn are going to be given by 1 upon the period, which is t0, times the integral over the period. Now over the period we can do it between τ upon 2 to minus τ upon 2, because from τ upon 2 to τ is 0, and from minus τ upon 2 to minus τ is going to be 0, so we've got it over that whole period there between τ upon 2 and minus τ upon 2. And the function is just going to be a height of 1, and that's times e to the minus I n omega naught t by dt. So whenever we integrate that, we're just simply taking the minus I n omega naught down to the bottom line, so it becomes minus 1 upon I n omega naught e to minus I n omega naught t from τ upon 2 to minus τ upon 2. And then for the value of t, we're putting in our τ upon 2, so the first term there simply comes minus 1 upon I n omega naught e to minus I n omega naught τ upon 2, and then it's minus this next term, which is minus here, so those two minuses cancel out, and also whenever you place the minus τ upon 2 in here for the t, the minus cancels there with the minus, so you end up with a plus sign 1 upon I n omega naught and e to the I n omega naught τ upon 2. So we take out the common factor 1 upon I n omega naught t naught, and it gives us e to the I n omega naught τ by 2 minus e to the minus I n omega naught τ by 2. Now we know we've seen this identity here before, and you can see that this term, this here, is roughly in this same form except for the fact of 2i. So what we can do is we can multiply this side here by 2i, the 2 remains and the I cancels with the I, and you end up with your sin n omega naught τ by 2. Now if we multiply the whole thing by τ by 2 upon τ by 2, just a little trick to get it into the format we want, then we'll end up with τ upon t0 times sin n omega naught τ upon 2 all upon n omega naught τ upon 2. So this is of the form sin x upon x, which is our sinc function. t0 is our period, τ is our pulse width. So let's have a look at this in a graphical format on the next slide. So this is our graphical representation of that function sin n omega naught τ upon 2 all upon n omega naught τ upon 2. So it's really of the form sin x upon x. The functions of the sine form sin x upon x are given their own function name. They're called sinc functions. So this is the sinc function here, where our x is n omega naught τ upon 2. And you can see that this function here is symmetrical. Also note that the axis here is a discrete axis, so that's the frequency omega naught and it's integer multiples of that frequency, so that's n omega naught. So each line up here represents a rotating phasor, and we'll see that whenever we look at it in 3 dimensions. So what to note about this here is that we have that axis n omega naught, so that's a function f of n omega naught. The height here of the largest phasor is going to be given by tau upon t naught, and the crossover point here is going to be given by 2 pi upon tau, and the next one will be 4 pi upon tau, so it'll be 2n pi upon tau will give us the crossover points. So the thing you notice about this here is that in the time domain, this function is a continuous function, it's periodic, and it's also an even function. So whenever we find the Fourier series equivalent of it, the sinc function here is going to be a discrete function. It's discrete in frequency, but still going to be periodic, and it's also going to be even. So let's look at this in a 3-dimensional approach, and I think this will add a bit of extra information. So I've drawn it out in 3 dimensions here. So the time domain I've just left as it is. It's just a function of time, but we're making an assumption it's not just that single function, there's actually a periodic wave, okay? So whenever we find the Fourier series equivalent to that, we'll have the real axis here, an imaginary axis, and we'll have our n omega naught. So we can think about each of these components here as phasors rotating round about this n omega naught axis. So they can rotate round, say, in a clockwise direction, or at the other side here on an anti-clockwise direction. But because this is a real even function, we don't have any imaginary component, we only have a purely real and even components. So if we had an imaginary component, it would be equivalent to having one of these phasors, say, sitting at a different angle, say this angle here, and this one, say, a different angle, say here, and they would be rotating round about this axis, the n omega axis. Now the thing to note here, and we'll cover in some of the later videos, is that if we were to add a time delay to this signal here, so instead of the function f of t, we would have f of t minus tau, and tau would be a time delayed version of this function. Well, a delay in time adds linear phase on in frequency, which really means that when we delay something in time, we start rotating all of these phasors, and they'll start rotating round in a clockwise direction, or on the other side, an anti-clockwise direction. But we'll get to that in later videos. So let's have a look in the next slide, and we'll try to explain the kind of ethos that we're going to be working through the rest of this course, as far as a graphical approach to the Fourier series and transform or Laplace transforms are concerned. So what we have here is a 3D representation of our Fourier series. Now, if we have the square function here, so that's the time axis here, that's a function of time, and this is a real even periodic square wave that we found the Fourier series equivalent for. Now over here, this is the n omega axis, so this is the frequency representation of this time domain signal, and it's a sinc function, and you can see that each of these represent a rotating phasor. So what we have here in the centre is the cos n omega naught t surface. Now time is continuous, so that's the t part, and the frequency is discrete, so that's the n omega naught, so it's cos of n omega naught t. So what we can do is we can actually just draw that function out. So that function there, it would be a DC term in the centre, and at this point here we'd have an amplitude of this phasor, but we'd only have one part of that phasor, and it would be the cos omega t part. And the same with this one, there would only be one part of that phasor, would be cos omega t part. And the same all the way along, in discrete lumps, we'll have the cos omega t. Now the reason we don't have the sine omega t is because this is a purely even function. And if it's an even function, it doesn't have any odd parts, so it doesn't have any sine omega t parts to it. So it means that this e to the in omega naught t, there's only one part of which is the cos omega t, so we can draw it out like this. Now if it turns out that the function that we're going to use is, say, purely an odd function, then we wouldn't have a cos omega t surface, we would have the sine omega t surface. If the function had both parts, so that it wasn't neither purely even or odd but a mixture of both, then we would have to have the two surfaces, which would be a cos omega t and a sine omega t surface, but that would be difficult to represent here, so we'll just look at it in terms of a simple function here of a real even function for the moment. So then you can see that these phasors here, there's just one part of it which is the cos omega t, and whenever we're doing our Fourier series representation, we're going from the time domain and we're heading towards the frequency domain. So you can see that in this instance here we're integrating with respect to time, which is a continuous variable, but if we were to come from the frequency domain back to the time domain, then we would be summing up these individual components, because it wouldn't be continuous in the omega axis, it's discrete in the omega axis. So a bit to take in there, but that's something that we'll get through and you'll see occurring again and again in the rest of the videos. So thank you for listening and goodbye.